Okay, so today's tutorial, the objective of today's tutorial is to make you all masters at finding instant centers. And I'm going to introduce a few techniques, maybe some tricks that I like to use just to keep my work organized. And hopefully that helps you when you're solving similar problems. This is my last tutorial, I think, for this term. Next week, someone else is going to take over. I'm sad too. But I'm sure you'll be in good hands. Yeah, we'll try to keep everything, all the continuity going with like tutorial recordings and everything. So hopefully that works out. Okay, so there's a lot of content to cover today. So let's just get right into it. Okay, so I'm going to try writing on a tablet today just because the diagrams can get a little crazy and we want to do I want to be able to use a lot of different colors to keep things clear. So we'll give this a go. Okay, so first of all, guys, let's settle down a bit here. So first of all, Professor Diller gave you the definition of an instant center in class. So let's just review the definition of an instant center again. So an instant center is the point. You don't have to write this down if you already have it in your notes. The point at which two bodies or links have identical velocity. Identical linear velocity, to be specific. And that's relative to each other. Apologies in advance if my handwriting is hard to read. I can clean it up. I can try to clean it up if people can't read it. So the key points here is it's a point. Okay, it's just one point. And they have identical linear velocity, relative linear velocity. So that's the important part. So they can both be moving at that point. They just have to be moving in the same direction at the same speed. The relative angular velocity can be non-zero. Relative angular velocity can be non-zero. Okay, so that's the definition of an instant center. And the reason this is useful is because it allows you to calculate the velocity of different points fairly easily. So if you have the base link, which is like the fixed reference frame, you can always be able to calculate the velocity of any given point relative to the fixed frame. And you can see why that would be really useful. Like if you have a link and you know where its instant center is relative to the ground, you can just know right off the bat where the velocity of any point on that link. Okay, and the number of instant centers. So we use this symbol P for instant centers. The number of instant centers is given by this formula, where n is the number of links. Number of links. So what this formula tells you is basically all the different ways that you can create a pair out of the links that you have. And it doesn't really matter what order the pair comes in. So if you have a pair of link 1 and link 4, that's the same thing as a pair between link 4 and link 1. Okay, so next, I want to give you sort of like my process for solving instant centers, basically a procedure. So step one, let's say to find instant centers. Oops. To find instant centers, step by step. Step one, list out all the ICs. So this is just listing them out, like P11 or P12, P13, P14, P23, P24. You're literally listing them out. And you should have the same number as dictated by this formula up here. Well, not really step 2. Step 1.5 is to check them off as you solve them. Okay, so that's just a trick to help you keep track of which ones you found, which ones you still need to find. And it helps you also identify how to find the ones that you're missing. And how that works is something I'm going to introduce later. It's sort of like a theorem that someone discovered, but we'll get into that in a bit. Okay, so that's step 1, is to list out all the ICs and check them off as you find them. Step 2, we start with the easiest ones. Start with kinematic pairs. So if you remember from yesterday's lecture, turning pairs, sliding pairs, turn plus slide, rolling, those all describe exactly where the instant center should be for the relation between those two links. And so right off the bat, you can just work through your mechanism, look at all the kinematic pairs that exist in that mechanism, and find the instant centers associated with those kinematic pairs. Okay, so that's step 2. Step 3 is, then we look for the two velocity vectors on the same link. Two velocities on the same link. So this really works if you're referencing to the ground link. Apologies for my writing again. Reference to the ground link. So if you remember from class, this is where if you have a body and you know the velocity of one point, and let's say you know the velocity of, I don't know, another point, maybe like this or something, then you can use the method where you draw perpendicular lines and see where those perpendicular lines intersect. Right? So in this case, this point here would be the instant center. And then the hard part is the last few instant centers. So for these ones, it's a bit trickier. You can try what's called, what's going on here? You can try inversions. I think Professor Diller mentioned this in passing. Inversions are where you take a link that isn't the ground link, but you pretend it is. And that allows you to find instant center sometimes. Or something we call Kennedy's theorem. Or Kennedy's theorem. And Kennedy's theorem is really powerful, but I will get into that after the following example. So Kennedy's theorem, stay tuned. Okay. So using this process, let's try an example. Does anyone have any questions about this right off the bat? No? Okay, good. Okay, so let's try an example of a 4-bar mechanism. Super straightforward, super simple. You don't have to draw it exactly the same way, just something that roughly resembles it. Okay, so here we have classic 4-bar mechanism. let's number the links. So ground is 1, 2, 3, 4, back to 1. OK. So first, let's list out all the instance centers that could exist. How many are there? So we have our formula, P equals n times n minus 1 over 2. That's 4 times 3 over 2 is 6, right? So we should have 6 instance centers to find. And to list them out, I don't know if there's a good way to do this. You just sort of start from 1, I would say. 1, 2, P1, 3, P1, 4. And then you go from 2, so P2, 3, P2, 4, and then P3, 4. So those are our 6 instance centers, right? It's all the different ways that we could pair up 2 links in this mechanism. Later, I'll show you another way that you can use to list out all the instance centers, especially when you have a lot of links. It might start to get a little confusing about how to list them all out, but there's a really simple geometric method that you can use, and I'll show you that later in the tutorial. The reason I'm not showing you now is because it has to do with Kennedy's theorem. It's very useful. OK. So what do we say as the next step in our procedure? So we've listed out all the instance centers, and we're going to check them off as we find them. So now let's do the kinematic pairs. Okay? So luckily, in this case, all the kinematic pairs are turning pairs, which makes things really simple. So we've got 4 turning pairs here, right? 1, 2, 3, and 4. And basically, the location of the turning pair is the same as the location of the instance center that those 2 links are a part of, right? So the turning pair here between 1 and 2 is P1, 2. That's the instance center between link 1 and link 2. And intuitively, you can kind of see that because link 2 is only rotating about that point, right? So link 1 is fixed, and link 2 is rotating about that point. So it makes sense that the instance center between those 2 links is at that point. Similarly, we can just list these out, P2, 3, P3, 4, and P1, 4. You could also write P4, 1 here, but I like to keep the smaller number first, just for organization. They're the same thing. OK, so that's the kinematic pairs all done. So we're done with step 2. OK, and I said we were going to check them off as we find them, so I'm just going to use the highlighter to highlight the ones that we finished. So we did P1, 2, P2, 3, P3, 4, and P1, 4, right? So now we're just looking for P1, 3 and P2, 4. OK, so the next step in our procedure here, actually, any questions so far? No, pretty easy. OK, so the next step is 2 velocities on the same link. And that's always referenced to the ground link. So to do this one, let's just try and draw the velocity of some turning pairs. So this turning pair here between link 1 and link 2, that's not moving, so we don't have to draw that. We know that the velocity of this turning pair between link 2 and link 3 has to be perpendicular to link 2. So it has to be in one of these 2 directions, right? And that's because link 2 is rotating about this fixed point down here. So we know that the velocity there has to be perpendicular there. And we can say the same about this point between link 3 and link 4. It has to be perpendicular to link 4. So it has to be along that direction. OK, so that's the velocities. So this is like a v question mark. It could be in this direction. And we know that the instance center, so I'll just back up a bit. So these points here, those are the two endpoints on link 3, right? Those are 2 points on link 3, and we know the rough velocity direction of those 2 points. And so using the method that Professor Diller showed in class yesterday, if you draw the perpendicular lines to those velocities, okay, so this is perpendicular, these are all perpendicular, and then we're drawing the line that I showed in blue, that's the line that's perpendicular to the velocity direction. And that allows us to find this instance center up here, right? The intersection of those 2 lines. So the intersection of those 2 lines is P13, right? Because we now know the velocity of 2 points on link 3, or at least the direction of them. And that's all relative to ground. So that's why it's the instance center between 1 and 3, P13. So let's highlight that. We're done with P13. Any questions about this? Yeah? Okay, yeah, so the question is about how do I know the direction of these green velocity vectors, is that right? Yeah. So let's look at link 2. I'll just draw link 2 sort of in isolation here. So this is link 2. So we know that link 2 has to be rotating about this base point here, right? And if link 2 is rotating about that base point, then the velocity of any point on link 2 on the link itself has to be perpendicular to link 2, right? Yeah. So if link 2 had sort of like another, I don't know, some weird projection coming off like this, then we would have to draw this line, and we would know that the velocity is like perpendicular to that. Okay? So that's how we know the velocity of the endpoints of link 3. Okay, so now the last one we're chasing down is 2, 4. So the instance center between links 2 and 4 is kind of tricky, right? Because none of the links involved are ground links. And there's no kinematic pair between them either. So in this case, we can let's try inversions, okay? Oh, and yeah, so we can't use the 2 velocity method either, because we don't really know how the velocity of the points on one link look relative to the other link. It's a bit hard to visualize that. Yeah, question?
Yeah, so I'm very sorry, I know you said this, but for P13, I'm not sure why did it call it P13. To me, I thought, why not call it P24 since it runs along 2 and 4. So to me, it was sort of counterintuitive.
Yes.
Can you please explain that again?
Of course. So the question is, why is this instance center up here P13 instead of like P24? So P13 means it's a relation between the ground link and link 3, okay? And these green velocity vectors that I drew in here, those are the velocities of the endpoints of link 3 relative to ground. So if those are the velocities of link 3 relative to ground, then it makes sense that it's the instance center between ground and link 3. I hope that makes sense.
Yeah, it makes sense. Thank you.
Okay. Okay. So I know inversions haven't really been covered in class very much, but like I said, inversions are just pretending something else is the base link. Okay, that's all an inversion is. You're pretending something else is the base link. Okay, so let's try that. Maybe we can try that with links 2 and 4. Or sorry, let's try making link 2 the base link. So if I redraw the mechanism here, but this time I take link 2 as the base link. And what used to be, oh geez, it's hard to draw straight lines here. What used to be the ground link is now a free moving link. Oops. So now the mechanism looks something like this, right? It's the same mechanism, but instead of link 1 being the ground link, I've made link 2 the ground link. Okay. So now that link 2 is the ground link, does anyone have any guesses about which of these three, or which of these two methods we can use? Kinematic pairs or two velocities on the same link? Any guesses? Yeah? Two velocities on the same link? Yeah, I agree. The two velocities on the same link method works really well here, right? Because the two velocity method works well when you're trying to reference something to the ground link. And now that we've made link 2 the ground link, and we're trying to find the relation or the instance center between link 2 and link 4, it works that we would use the two velocity method, right? Okay, so let's try to find the velocities of the endpoints of link 4, or at least the directions of them. Using the same idea as above, link 3, the endpoint of link 3 that connects to link 4 has to be perpendicular to link 3, right? So it has to be in one of these two directions. And the endpoint of link 1 has to be moving straight up or straight down because it has to be perpendicular to link 1. Okay, I'm going to have to move this. Okay. Oh, all the color's gone. I'll just trace it. Okay. And we know that by drawing the two lines that are sort of perpendicular to those velocities, we can end up with the instance center just by finding the intersection of those two lines. So way off over here, this is P24. Okay? Sorry, you're going to have to forgive a little bit of line bending here. Just want to recreate it on this diagram up here as well. Just pretend this line is straight. No one saw anything. Okay, great. So now we've found all the instance centers. Does anyone have any questions about that last one? I know that last one is probably the most confusing one. Yeah, question? Do you want to repeat which line is straight? Yeah, this line here. This is supposed to be straight. Pretend that's straight. I just don't have enough room on the end of the page to make it straight. Okay, any other questions? Yeah?
Under what condition that we can use the inversion?
I'm pretty sure that you can use inversions anytime, but it's not always useful. And once we learn Kennedy's theorem, I personally find it easier to simply use that instead of inversions. For me, it's easier to think about. But it's a trick for your toolbox. Okay. So now let's learn about Kennedy's theorem, this thing that I've been hyping up so much. Okay, so let's take a look at all these instance centers that I found. And I want you to notice there's a few areas where a number of instance centers line up on the same line. Specifically, there are a few instances where 3 instance centers are all on the same line. Let's try to list them out. Okay, so we're listing out the instance centers on the same line. Okay. Does anyone want to help me out here? What are some instance centers that lie on the same line? Yeah?
P12 and P23.
P12, P23, and if you go even further, P13, right? Okay, so that's a good one. P12, P23, P13. P12, P23, and P13. Okay, so that's one of them. Another might be P13, P34, P14, right? Those are 3 instance centers on the same line. P13, P34, and P14. There's 2 more that I think exist. Let's look at this one. So we're pretending this line is straight, right? P24, P23, P34, P24, P23, P34. What did I say? P24. Right? And you could go on listing these, but these all have a trend. So let's look at what links are involved. What links are involved in all these triplets? So here we have link 1, 2, and 3. For the second one, we found 1, 3, 4. This last one, 2, 3, 4, right? So this is showing you something about Kennedy's theorem. And what Kennedy's theorem says So Kennedy's theorem is that for any 3 links, the 3 ICs associated with those links lie on the same line. So this is a pretty powerful theory. If you take just any 3 links and you find the 3 instance centers associated with those links, they will always lie on the same line. I need to move this aside. This comes later. I'll come back to that. Actually, I wonder if I can just move it to a different page. Hang on. Okay, we're back. Okay. And I also told you earlier that I have it's sort of a useful tool or kind of a trick that you can use alongside Kennedy's theorem, and it's also a way to list out all the different ICs. So that's a concept called the auxiliary polygon. The auxiliary polygon. Okay, so I'm going to put these 2 together, and we're going to look at an example in a second. I just want to sort of lay the groundwork for that. So to use an auxiliary polygon, you draw a polygon with the same number of vertices as links in your mechanism. Okay? So 3 links, you draw a triangle. Five links, pentagon. Okay? Next, you number all the vertices from 1 to however many you have. Okay, so let's try these first 2 steps. It's not quite done yet, but let's try the first 2 steps with our 4-bar mechanism. So we have, it's a 4-linkage mechanism, right? So let's say for the above 4-bar, we have a square, right? 4-sided polygon. And we're just going to number the links, or number the vertices. 1, 2, 3, 4. Same number of vertices as links in our mechanism. Then the next step is connect all the vertices with lines. Connect all the vertices with lines. So this just means every vertex should be connected to every other vertex with a line. So in this case, the missing ones are between 1 and 3 and between 2 and 4. Right? So we end up with this like box with an X in it. It would look different if you had a different number of sides polygon. Okay, so now we've drawn our auxiliary polygon. And in this auxiliary polygon, all the connecting lines or sometimes called edges, represent ICs. So every single line there connects 2 links, right? And between every 2 links, there's an instant center. So all those lines represent an instant center. And in this case, there's 6 of them. Okay, and now how this ties in with Kennedy's theorem. How this ties in with Kennedy's theorem is that all the triangles represent 3 ICs that obey Kennedy's theorem. Okay? So if you take any 3 vertices of your polygon and you look at the triangle associated with them, then that triangle has the 3 instant centers that obey Kennedy's theorem. And that goes for all the triangles that you could create. So if we just look at the triangle between 1, 3, and 4, this gives us P13, P34, and P14, right? And I do believe if we scroll up far enough, that was one of the instances we identified, right? Where all the 3 instance centers lie on the same line. And you could also do that with link 2, 3, 4, the triangle there, or 1, 2, 4. All of the triangles in there that are formed by joining 3 of the vertices will obey Kennedy's theorem. Okay, and this will probably be a little more clear once we go through an example. So this is a tool that you can use to identify instance centers. And it's very powerful, and I'm not sure if there's any case where I'd rather use inversions than this. But let's look at an example. So here's an example. It's a slider crank mechanism. Okay, so we have this slider crank mechanism. And we had our procedure from before. Let's use it this time, but we'll use Kennedy's theorem and the auxiliary polygon instead. Right? So we start by numbering the links, as always. Hope you're all masters at this by now. 1, 2, 3, 4. 4 links in this mechanism. Okay, let's draw the auxiliary polygon for this. Right, so there are 4 links, so we're looking at a square. And we can number the vertices, 1, 2, 3, 4. And we can connect all the vertices with connecting lines. Okay, so we have the same square with an x in it that we had before. And so now, instead of checking off each instance center as I go and find them, I'll just change the color of the line or highlight it or something. So if I was to find the relation between, or the instance center between link 1 and 2, I'll just change the color of that line. In your notes, you can highlight it or something. So that just tells you which ones you found already. Okay, so let's go through. We start with the kinematic pairs. Here's P12, P23, P34, and P14. Remember the sliding kinematic pair, when you have a straight sliding surface, that instance center is located off at infinity, right? Perpendicular to the sliding surface. So P14 is off at infinity. Okay. So let's just indicate that we solved those. So P12 I found. P23 is right here. P34 and P14, right? So just like before, we're looking to solve for P13 and P24. So any line that I've left black here is one that we haven't found yet. So we did all the easy ones with kinematic pairs. Now we'll use the 2 velocity method to try to find P13. Remember, the 2 velocity method is most useful when one of the links is ground. So P13 is a good candidate. So just like before, the velocity of this point between link 2 and link 3 has to be perpendicular to link 2. And this point between 3 and 4 has to be sliding left and right. Yeah. So if we draw the lines perpendicular to that velocity, we find that P13 has to be here. Okay. So we found P13. Let's change the color of that line. Now we're only looking for P24. But already you can see, and if you look at our auxiliary polygon over on the right here, the triangle between 1, 2, and 3, or this one, 1, 2, 3, we already have all those, right? So let's see if those obey Kennedy's theorem. So P12, P23, and P13 are the three edges on this polygon here. And they are all indeed on the same line, right? And you could say the same about the other triangle that we've solved, 1, 3, 4. That's P13, P34, P14. Those are also all on the same line, right? So far everything checks out. Kennedy's theorem seems to be obeyed. And for this last one, let's use Kennedy's theorem, okay? P24. Let's try to use Kennedy's theorem to solve for that one. So the trick with Kennedy's theorem, this might take a bit of practice to get your head around, but the trick with Kennedy's theorem is you want, let's say, to use Kennedy's theorem, to find an IC, you need two triangles where the IC in question is the only unsolved edge. Okay? To use Kennedy's theorem to find an instant center, you need two triangles where the instant center in question is the only unsolved edge. And what do I mean by that? So if you're looking at this auxiliary polygon here, we are looking for P24, this sort of like diagonal line from top left to bottom right, right? So if you want to use this trick says you have to find two triangles that have that as one of the sides, but everything else in those two triangles has already been found. So I think this case is a little more straightforward because there's only two triangles that have that as an edge. So in this case, we have 2, 4, 1, and the opposite, 2, 3, 4, right? And we've already found 1, 2, and 1, 4, and we've already found 2, 3, and 3, 4. So now we have these two triangles, right? And you can see there's two triangles where the instant center in question is the only unsolved edge. So now we know that we can find this instant center 2, 4 using Kennedy's theorem. And the way that you do that is kind of like the two-velocity method. You're going to end up drawing two lines, and where they intersect is the instant center. So let's see. So let's look at this left triangle first, 1, 2, 4. So link 1, 2 and 1, 4 have been found. 1, 4 is off at infinity, and 1, 2 is at this turning pair at the bottom left. So if we draw a line going from that turning pair off to infinity, remember, if a point is located at infinity, it's really more indicating a direction. So this sort of vertical line here, where I drew a P14, it can slide left and right. So if you were an imaginary person standing at point P12, and you're looking at P14, you'd be looking at the same direction, just straight up. Okay, so we know that P24 has to be somewhere along this new line that I've drawn, right? Somewhere along there, but we're not sure exactly where yet. So let's look at this second triangle. It says P23, 34, and P24 all have to be on the same line as well. So P23 is at this turning pair here, and P34 is at this turning pair down at the bottom right. So if we draw a line connecting those 2 points, we can see there's an intersection, right? The intersection of those is right here. So this must be where P24 is, right? So that's why you need two triangles, is because each triangle gives you one line. And so you need two lines to intersect in order to find the instant center. Okay, so this is a very powerful technique. Using Kennedy's theorem along with the auxiliary polygon should allow you to find basically any instant center. Yeah?
Sorry, could you repeat why you do that line to infinity?
Yes. So this, you're talking about this line here, right?
Yeah.
Okay, so the reason I drew this line that I highlighted in green is using the triangle on the left down here. So I know that P12, P24, and P14 all have to be on the same line. So the line, this is the line joining P12 and 14. So 12 is this turning pair down in the bottom left, and P14 is off at infinity. So that's why that line just goes straight up, because P14 is just in the vertical direction. Okay, so yeah, question?
Isn't like P14 above link 4? Why are you drawing it above link 1 over there at the pivot point?
Yeah, so the question is, isn't P14 above this slider, right? So why am I drawing P14 sort of like off at infinity on that side as well? Well, imagine you and I were looking at a point on the horizon, basically infinity distance away. We'd both end up looking basically in parallel directions, right? We wouldn't look like crossed. I wouldn't draw the line that I've highlighted in green, I wouldn't draw it any other direction than parallel or like straight up, because if I did, then that point wouldn't be at infinity, right? If a point is infinite distance away, then all the people beside you looking at it, we're all looking the same direction. Does that make sense? Okay. Okay, so that's your first introduction to Kennedy's theorem. Any other questions before we take a break? No questions? Okay, if you have any questions, you can come up, ask me. Let's take a break until, let's say, 11:10. Okay, so it's finished our break time here, guys. We're going to get into a really meaty example. Okay. All right, guys, let's settle down. Let's settle down. Okay. So we're going to tackle this example from the handout. And we're going to try to find all the instant centers in this diagram. So that's our goal. Find all ICs. And we'll just do as many as we can in the time that we have. Okay, so I remember I gave you the procedure that you should follow whenever you're trying to find ICs, or maybe just my suggestion for how to do it. Yeah, if you don't have a handout, there's more at the front. They're also on Quarkus. So first we're going to list out all the ICs or use auxiliary polygons, right? So let's see how many links are in this. It looks like it's already numbered for us, and it looks like there's 6 links. Okay, so 6 links. So that means we're looking at a hexagon. Our auxiliary polygon is going to take the shape of a hexagon. So we're going to draw a little hexagon here. We can number it. 1, 2, 3, 4, 5, 6. And then we have to connect all of the vertices with connecting lines, right? So let's start from 1. We have 1, 2 already done. 1, 3, 1, 4, 1, 5, 2, 4, 2, 5, 2, 6, 3, 6, 3, 5, and lastly 4, 6. It gets crazy. I know it gets crazy.
Robin,
Yeah.
do it again. You just did it kind of fast.
Okay, yeah. Just hit the undo button. Okay. So the easy way to do this is just start from number 1, right? And just go clockwise around and fill in any lines that don't exist yet. So from number 1, we already have 1, 2, and just proceeding clockwise from there, 1, 3, right? Clockwise again, 1, 4. Clockwise again, 1, 5. And 1, 6 already exists. Let me see if I can make this a little bigger. Oh, that's better. Okay, so now we're done with number 1. We can go on to number 2. So just from 2, we proceed clockwise. So 2, 3 is already in. 2, 4 hasn't been drawn yet. 2, 5. 2, 6. Remember, we're just going clockwise. And 2, 1, it's already there. Now for number 3. 3, 4, going clockwise. 3, 4 already exists. 3, 5, it's not drawn in yet. 3, 6, it's not drawn in yet. 3, 1 is already there. And 3, 2 is already there. Then from 4, simple, same procedure. 4, 5, 4, 6, we're just going clockwise. 4, 1, 4, 2, and 4, 3, they're already there. And I think that's it, right? I don't think there are any more. If you go from 5, 5, 6, 5, 1, 5, 2, 5, 3, and 5, 4, they're already all drawn in. Yeah? Okay, so all of these lines in this auxiliary polygon represent instant centers. And the number of them you can find with our good old formula. The number of instant centers is found with this formula. So that's 6 times 5 over 2. What was that, 15? So there should be 15 instant centers. Okay, and just like before, we're going to change the color of the lines as we find the instant centers. Okay, so step 1, like always, we're going to start with the kinematic pairs. And the turning pairs are the easiest. So right here we have P13. Over here we have P12, right? It's the turning pair between link 1 and link 2, so it's P12. Over here we have P56. So let me see if I can make this diagram a little bigger. Hope this works. Oh. Okay, that's better. Okay, so let's just shade those off before we do too many. So P13, we found P13. P12 we found. And P56. So those are just using turning pairs. let's see, there's a couple more turning pairs. Over here, oops, let's use red. Over here we have P24. Right? It's the turning pair that links 2 and 4. And over here we have P35. Okay, so those are all our turning pairs. Let's just note those down on our auxiliary polygon. So P24, got this line here. And P35, this line here. So our goal is to basically eventually turn this whole spider's nest into green lines. Okay, so those are all the ones with turning pairs. Those are kind of easy ones. The easiest, I would say. Next, let's look at the other kinematic pairs. We've got 2 sliding connections, right? So this one here between link 1 and link 6. Sliding connection means the point is off at infinity when the sliding surface is straight. So we can just draw a line and say P16 at infinity. And it could be up or down, actually. We don't know if it's at infinity in the positive or negative direction. But it doesn't really matter because whenever we draw lines for Kennedy's theorem, they extend in both directions. Okay. And the other sliding pair is here between links 3 and 4. So this one's a little tricky to draw because you have to get it sort of perpendicular to the sliding surface. Let's draw something like this. And that's perpendicular here. And this is P34, also at infinity. Right? It's a sliding joint. And the sliding surface is straight, so that point is located at infinity. Okay, let's note those down on our auxiliary polygon. So P16 and P34. Okay, that's a good start. Okay. Any questions on those? Yeah.
Could you label that collar thing on link 3 as just 1 2-degree of freedom joint or kinematic pair rather than just 2 1-degree of freedom?
If you wanted to analyze how this mechanism moves, then you could. But with a question like this, the point is with the links as they are. What are all the kinematic pairs, right? So we're trying to find all the kinematic pairs with the mechanism that we have, not one that's equivalent. And it matters because it changes the number of kinematic pairs there are when you have more or less links.
So like, how do you know it's not a 2-degree of freedom joint after collar?
Well, it behaves the same as one, but it's physically not the same. Yeah, so you know, if the question was just about like limit positions or something, then you could model this joint here as like a 1 2-degree of freedom pair with one less body. But the question is about instance centers, so we need to consider all the links that we have. Okay. So this is where it gets a little bit tricky. It's definitely not as straightforward as the case with only 4 links, right? It gets like exponentially harder when you have more links, because it's harder to spot all the different triangles that you have in this crazy mess of the auxiliary polygon. So it becomes a little bit of a trial and error. It's almost like Sudoku puzzles where you just go through, does 1 work, does 2, does 3? And you just sort of try them all, and eventually you find them. Okay, let's try Let's try P14. I have the benefit of already knowing which ones work. Let's try P14. So remember what I told you about finding candidates that work well with Kennedy's theorem, right? We are looking for two triangles where the instance center is the only edge of those two triangles that we haven't found yet. Yeah, question?
Yeah, I'm wondering why we don't like use the velocity method to like narrow it down more before we rely.
Yeah, we could. Actually, fine, let's do that. No, that's definitely good practice. I think I just wanted to get to Kennedy's theorem, but you're right. That's a better method because it's easier. Okay, so let's look at the velocity of a bunch of different points here. Let's look at point C. So point C is on link 3, and it's rotating about link 1, right? Okay, so it's moving in one of those two directions. And this point here between link 5 and link 6 has to be sliding left and right. So now we know two velocities on link 5. And if we draw perpendicular lines from those two, we find, okay, I'm just going to erase my writing down here. I hope there's enough room on your printout. I tried to position it so that it works. So down here, what instance center would this be? Does anyone have a guess? P15? Yeah, P15, right? Because we found the velocity of 2 points on link 5 relative to ground. And using those two velocities with the two velocity method, we can find this as P15. Let's shade that off in our little diagram. What would be another good candidate? Do we see any other good candidates for the two velocity method? Link 2. We already have link P12, right? Or you mean this point here?
Yeah.
So if we find the velocity of this point, it's perpendicular to link 2. And let's think, what would that be useful for? We already have P13, so it's not very useful for P13, especially since this point isn't even fixed on P13. It is fixed on link 4, but we don't really know the velocity of any other point on link 4, right? So in this case, the two velocity method doesn't quite work for link 4 because we only know the velocity of one point on there. Okay, so it looks like at this point we've exhausted our options for kinematic pairs and the two velocity method, unless we want to try inversions or something. But now let's try Kennedy's theorem. Yeah? Okay. So looking at this diagram here, it looks to me like there are two triangles that might work. One is 1, 2, 4. Right? 1, 2, 4. That's a triangle with only one unsolved side. And let's focus in on this line between 1 and 4. Do you see any other triangles that involve the edge 1, 4, where the other two sides are already solved? Yeah? 1, 3, 4? 1, 3, 4. One, 3, 4. Yeah, that looks like it works, right? We've now got two triangles where 1, 4 is the only unsolved side. So we can try to use Kennedy's theorem to find P14 using these two triangles. Okay, so let's start with the one on the left, 1, 2, and 2, 4. So 1, 2 is at this point here, and 2, 4 is located on this diagonal slider. If we draw a line extending from those two, remember the line goes in both directions. We're not sure where on this line it is yet, but we know that P14 has to be somewhere on that line. So P4 is somewhere on this new blue diagonal line that I've drawn. Now let's look at the right side triangle, 1, 3, and 1, 4. Okay, so 1, 3 is down here at this lowest pivot point. And 3, 4 we already found is off at infinity, right? So the question is, how do we join this point with a point that's at infinity? Well, remember that this line here, the line that I just highlighted, it's more of a direction, right? So we can translate that perpendicular to its direction as long as we keep the direction the same. Or in other words, we can, from any point, we can just draw in that same direction to reach P34. So I would like to undo this highlight. Okay. Okay. So from 1, 3 to draw towards P34, which is located at infinity, we just have to draw it in the same direction. And remember, this line also extends in both directions infinitely. Okay, so it looks like those 2 points intersect. Geez, voice crack. Intersect. I've been talking for like over an hour. My throat is very dry at this point. But now it's recorded and it's there for posterity. I'll just live with it. Okay, so this is P14. P14. All right, excellent. So we used Kennedy's theorem to successfully solve for P14. Nice. Okay. All right, I'm going to throw this to you guys. Any other suggestions on which one we should try to solve next? Someone raise their hand, yeah?
Can we do P26?
P26.
Yeah.
Using which triangles?
No, I mean, just like, we know the direction vectors for 2, but we also know where P16 is. So would that work if we just drew a line?
P16.
So the line of P16 to essentially where link 4 is. Or does that not work?
Well, the problem is that P2, if we're trying to find P26, we need to know something about like the relative velocities between 2 and 6, right? So because 2 and 6 are both moving, it's hard to visualize that. You could potentially find it if you did like an inversion or something, but personally I find Kennedy's theorem easier. I mean, if you're working through your problem sets and you find that inversions are working really well for you and you're getting the right answers with them, then by all means. But it's good to know both, actually, because then you can use one to check your work from the other. They should be consistent. OK, so any other suggestions about which one we should find next? Yeah? P36. OK. P36. Which triangles would you suggest?
136, 536.
136 and 536. OK, that looks like it could work, right? If we have P36, we could use 136 and 536. Okay, right? So now we've got two triangles where P36 is the only unsolved edge. So that looks like it could work. Okay, so let's focus on this upper one. P16 and P13. So let's see, P16 is located at infinity, and P13 is located at this base point down here. So if we just draw a line that connects those two, it's just vertical extending from P13. And now for the lower triangle, 5, 6, and 3, 5. Well, 5, 6 is located at the point of the slider, and 3, 5 is located at this turning pair here. So basically just extending link 5, where link 5 is the line of that lower triangle. So now we know that the intersection of those 2 points right here, that's P36. Okay, P36. So now we found P36. We can color that in. Okay, does that make sense? Any questions about that? Yeah?
Sorry, what was the line that's also intersecting? I kind of lost it.
Yeah. So the question is, what are the two intersecting lines for that one that we just did, P36? So we found these two triangles down here, right? And each triangle represents a line that we can draw. So one of the lines is joining 1, 6 and 1, 3. That's 1, 3 here, and 1, 6 is off at infinity. So it's just a vertical line coming from the lowest base point. And then the other line is joining 5, 6 and 5, 3. So P35 and P56 are these two turning pairs that are on link 5. So link 5 itself basically becomes the line. Yeah. Okay. Does anyone else want to volunteer a candidate that we can use Kennedy's theorem for? Yeah.
Triangle 5, 4, 3 and 1, 5, 4.
5, 4, 3 and 1, 5, 4. 5, 4, 3 and 1, 5, 4. Okay, so we're looking for P45 in that case, right? Okay, so if we're looking for P45, we can use, sorry if this is a bit messy here, guys, but 3, 4, 5. And the other one is 1, 4, 5. So these two triangles, 3, 4, 5 and 1, 4, 5, we can use to find P45. So let's look at 1, 4, 5 first. So P14 and 1, 5. 1, 4 is located at this point. We found that one. And P15 is down here. P14 and 1, 5. So it's somewhere along this line. Not sure where yet. And 3, 4 and 3, 5, where are those? So 3, 4 is off at infinity, and 3, 5 is here. So if we draw a line extending to infinity from 3, 5 towards 3, 4, then P45 is like way off, somewhere where these two lines intersect. Sorry, it's a bit messy. Yeah, so P45, somewhere up here. So you can see how this, these things can get pretty crazy. And this is where using your ruler is very handy. If you have like, one of these like right angle ruler things. They're also very helpful.
You go over that one again?
Yeah, okay, so someone's asking to go over that one again. So we're looking for P45. P45. And we found two triangles that work for that because P45 is the only unsolved edge on those two triangles. So starting with the triangle 3, 4, 5, we can join 3, 4, and 3, 5. So 3, 5 is here at this turning pair, and 3, 4 is off at infinity along sort of like this direction, perpendicular to link 3. So we draw a line, one line like that, and then the other line is 1, 4, 5. So 1, 5 we found down here, 1, 4 we found over here. Oops. And if we draw a line connecting those, then we can find the intersection of those two lines, and that gives us P45. Okay? So you can just keep following this procedure. It really works the same. Like once you understand Kennedy's theorem well and how to apply it, it's really quite formulaic, and I don't think it adds any there's no really Kennedy's theorem that's like more difficult than another. You would just keep going through this mechanism. So if you want, I could go through and solve all the ICs in this mechanism, but it's really the same process. Okay. So if any of you are confused about this, feel free to email me or come up after the tutorial and ask me questions. But let's just leave it there for now. So thank you guys. Thank you.